Okay, let's jump right in. We kind of left off last chapter calculating slopes of curves at different points. Okay, so if I asked you to take this function f of x, x squared plus 2x, and calculate f prime of 1, f prime of 3, f prime of pi, and f prime of square root of 2, that's asking you to find the slopes of f at those points. Okay, now what's involved in finding those values? Okay, well, what's involved is applying the definition of f prime of a to those 4 different points, and that would involve these 4 different calculations, okay, which are not incredibly difficult, but you can see it takes at least 4 steps of good work to get to some answers. Okay, f prime of 1, when you're all said and done, is 4. F prime of 3 is 8. Okay, and you don't have to write this stuff down here, but I'm just making a point that calculating these individual values for the slope of this same function at different points requires a little bit of work. Okay, now it would be very convenient to have a function. Okay, a function. Remember, a function is something that you plug something into and something comes out. Okay, it would be convenient to have a function that will calculate the slope of f anywhere I want just by plugging in an x value into this function. And that's what we're about to do here, is create that function and show you where that function comes from, so that you don't actually have to go through these same calculations over and over again for the same curve. I find it very useful as we move on in the course. All right, so we're going to take a similar approach to what we did a couple classes ago, except point A now is not going to be a stationary point. Point A is going to be allowed to move. So in general, the coordinates of point A are going to be x, comma, f of x. So that is my point. That's my x value that I'm going to be plugging in eventually down the road. Now, I need a second point to find the slope between these 2 points, and then we'll take a limit to make them very close together. All right, just like we did before, we're going to create a little bit of distance between point A and point B. And let's call this distance h. So what are the coordinates of point B? Well, if I start at x and I go h units to the right, then my x coordinate is going to be x plus h, which makes my y coordinate f of x plus h. Okay, what is the slope between these 2 dots? If I draw a line that connects point A and point B, the slope is going to be the change in the y values, which is going to be f of x plus h minus f of x. The change in the x values is going to be x plus h minus x, which ends up just being h. And to make these 2 points, A and B, as close together as we possibly can, we want this distance h to shrink to be almost 0. Okay, so we want h to approach 0, and in calculus, the mechanism that allows us to do that is a limit. So if we can calculate this limit, we will now have a function, okay, that does what we want it to do. What is the function going to do? Function that finds the slope, at least as far as the graph is concerned, slope in the real world, okay, or instantaneous rate of change. Saw this term used before. And the key point here for this function, okay, for any point x, comma, f of x. So in other words, I don't need to be doing specific locations when I start. I can create this function, and then once I have the function, I can just plug in x values to get the slopes or rates that I'm looking for. This function has a special name. It's called a derivative, because it is derived from the original function that we started with. Okay, so we call this the derivative of f of x. Now, here's where things get a little bit hairy. Calculus was invented, or discovered I should say, by two different men on two different continents at roughly the same time. So the symbols that we use in calculus come from two different locations, an English variety and a German variety. Each set of symbols has its uses in different contexts that make more sense. So we have to get used to different ways to say the same thing. So, to say the derivative of f, there's many ways. This one will make sense to you because it looks like something we just did a couple class periods ago. All right? One symbol for the derivative of f is to put f with the quotation mark and then an x. This is read, as you might guess, f prime of x. The difference between this and what you did before is that this is a function, not a number. Obviously, if you punch a number in for x, it becomes a number, it becomes a single slope. F and y are often interchangeable in mathematics, so another way to symbolize the derivative is to say y prime. The German notation looks like a fraction, and it should look like a fraction that is somewhat familiar to you. We can say dy over dx. That's another way to say the derivative of y, and it's telling you that x is the independent variable. These letters will change from time to time, but this still is a symbol for a derivative function. Okay, and then one we're going to use for the rest of the day is this one. If I just write d over dx, this is saying the derivative of whatever comes next. Okay, derivative of whatever comes next, and most of the time we're going to use f as our letter for function, and the f of x will be in there. So if you see this, this is telling you the derivative of this is whatever I write next. Or it's asking you, find the derivative of what's inside here. Let's do a basic example using this calculation. Okay, this is now specifically the curve f of x equals x squared. So we are looking for the function that finds the slopes of this curve anywhere I like. In other words, we're looking for the derivative d over dx of x squared. Okay, that's what we're looking for. How do we calculate this? Well, the definition says we take the limit as h goes to 0, f of x plus h. So what is f of x? F of x is x squared, so f of x plus h will be x plus h squared. We're inputting x plus h in for the variable x. So we have x plus h squared minus f of x. F of x is given, is x squared, all over h. These will always start off being 0 over 0, so some work's required on our part. In this example here, I'm going to go ahead and expand the numerator. You could also factor the numerator as a difference of two squares. Okay, so what do we got? We got x squared plus 2xh plus h squared minus x squared all over h. The x squareds cancel out, and we'll notice that every term left has an h as a factor. So we're going to go ahead and factor out h over h. I'm still taking a limit as h goes to 0, and I'm going to split this into two limits now. Okay, what remains when I factor out h over h? I have a 2x plus h to the first, and the denominator is now a 1. This first limit is 1. H over h simplifies to be 1. And now I'm at the plug-in stage. If I plug in a 0 for h, I am left with 2x. This is telling me that the function that finds the slopes of x squared is 2x. And all I need to do is plug in x values to get slopes. Let's go to GeoGebra and take a look at what this looks like. Okay, so we just found that the slope finder for x squared is 2x. This means that at 1, 1, the slope should be 2 times 1, or 2. And at 2, 4, which is point B, the slope should be 2 times 2, or 4. And at negative 1, 1, which is point C, the slope should be negative 1 times 2, or negative 2. So what does that mean? Well, for one thing, it means I can write the equation of some tangent lines and check my work to see if I'm correct. So if the slope of this curve at 1, 1 is 2, then I should have a tangent line that has equation 1 plus 2 times x minus 1. When I hit enter, what I would expect to see is a line that goes through point A that's going to be very, very tight to the curve near A. And when we zoom in, the curve and the line will look the same. Why? Because they have the same slope and because they both contain point A. Let's take a look. Okay, there's my tangent line. And now let's zoom in on point A. The more I zoom in, the more the red curve and the black tangent line start to become the same, or at least appear to be the same. There are still very minor differences, but as far as our human eyes can tell, they are the same. Okay, let's head back. Let's take a look at point B. If the slope is really 4, then the equation of the tangent line should be 4 plus 4 times x minus 2. All right, this next line looks pretty good. Let's zoom in on point B a little bit. And we can see even faster that the red curve and the black tangent line start to become almost exactly the same. Let's take a look at one more. If the slope at point C is really negative 2, then the equation of the tangent line there will be 1 plus negative 2 times x minus a negative 1, so plus 1. And that looks pretty good as well. Real quick zoom in on point C. And our tangent line and our curve start to just about overlap the more we zoom in. If you'd like to do some practice with the definition and calculating derivative functions, pause the video and try these 3 examples. The answers are going to be on the next slide, so if you're serious about that, really do pause it at this point. Now, what we want to talk about next is noticing some patterns here, because this calculation, while very useful in creating a function that finds slopes, can also be somewhat tedious to do over and over again. And there may be some ways to shortcut this as well. So we already have done the derivative of x squared is 2x. And if you had done these on the previous slide, then here's your chance to check your work. The derivative of x cubed ends up being 3x squared after you do the process for finding the derivative function. The derivative of the square root of x ends up becoming 1 over 2 times the square root of x. And I'm going to rewrite that slightly as 1/2 times x to the negative 1/2. Okay? My rules of exponents say that this is x to the 1/2 in the denominator, which can be moved to the numerator as a negative exponent. Now, the derivative of 1 over x ends up being negative 1 over x squared. And I'm going to rewrite that slightly as negative 1 times x to the minus 2. Again, using my rules of exponents, I can write x to the second in the denominator as x to the negative second in the numerator. Okay, so all 3 of these functions that you found the derivatives of are what are called power functions. They are x to a power, x to the second, x to the third, x to the half, and this would be x to the minus 1. And I want you to notice what the derivatives of these functions end up being. Okay, the derivative of x squared is 2 times x. The derivative of x cubed is 3x squared. The derivative of x to the half is 1/2 x to the negative half. And the derivative of x to the negative 1 is negative 1 times x to the minus 2. There's a pattern here, and I hope you notice it. The derivative of x squared became 2x, the 2 coming from this exponent. So this exponent comes down in front when you're taking the derivative, and that occurred in each of the examples. Here, the 3 came down in front. Here, the 1/2 came down in front, and here the -1 came down in front. That's not the only thing that occurred. In each instance, the exponent that you started with was reduced by 1. The 2 became a 1. The 3 became a 2. The 1/2 became a -1/2. And the -1 became a -2. This is not a coincidence. This is actually a pattern that we will use to shortcut the derivative process. Okay, we call it the power rule because we are taking derivatives of powers of x. So the power rule says that the derivative of x to any power n, okay, n is a number, becomes n times x to the n minus 1. Take the exponent down in front, subtract 1 from the exponent, and that is a shortcut to finding the derivatives of these type of functions. We're going to learn many shortcuts as we go to avoid doing this process when possible, but when we have no idea, we will go back to this definition. That's why it's important to know. Okay, next rule we need to look at is what's called a constant multiple rule. What does that mean? It means what happens if I have a constant in front of a function. What happens to that constant when I take a derivative? So we're going to go from the definition here and show you what happens. Okay? By definition, the derivative of c times f of x becomes c f of x plus h minus c f of x. These two terms both have a c, so I'm going to factor the c out and put it in front of the limit, because this limit has to do with h going to 0, and there is no c's in this expression that contains c. You'll notice here that what's left after the c is just the definition of f prime of x. So the short of the story is, if you have a constant in front of a function, and you're taking the derivative, this constant just goes along for the ride. You take the derivative of the function that's after the constant, and the constant remains out in front. Okay, real quick example is the derivative of 24x to the 5th. This rule says that that's going to be the same thing as the constant out in front times the derivative of the function after the constant. So, using the power rule, the derivative of x to the 5th is going to be 5 times x to the 4th. And now we can multiply the 5 and the 24 and get 120 x to the 4th. Okay, so very simple. You can just jump from this step to this step. Now that you know the rule, these numbers just get multiplied. You still subtract 1 from the exponent. Okay, then we also need a rule for sums and differences. So by definition, the derivative of a sum of two functions would be this. The limit as h goes to 0, f of x plus h plus g of x plus h minus f of x plus g of x. If we rearrange the terms a little bit, we notice that this portion right here is just f prime of x, and this portion right here is just g prime of x. So the short of the story is the derivative of a sum is the sum of the derivatives. Sort of like the derivative distributes over addition and subtraction. Okay, it's a convenient rule. It's very nice. We'll find out later that products and quotients don't work this way. But what does that mean for me? That means that the derivative of this big thing is the same thing as doing the derivative of each piece individually. So in other words, the derivative of 24x to the 5th plus the derivative of 5x cubed plus the derivative of 7. Now you're saying, hey, 7 is not a power of x. Well, it kind of is. We could write this as 7x to the 0, because x to the 0 is 1. 1 times 7 is 7. Now, we just did this one, so this is 120, 120 x to the 4th, plus, what's the derivative of 5x cubed? Well, it's going to be 15x squared. And what's the derivative of 7x to the 0 going to be? is going to be 0 times 7, which is going to wipe everything out no matter what's after this, so plus 0. And that's a little side note here. The derivative of any constant is going to be 0.